Good morning. My name is Kyrre Kausrud. I usually work at the Norwegian Veterinary Institute at the section for epidemiology. Currently also for the Norwegian Science Committee for Food and Environment, where I presented this short talk about spatial perspectives on GIS in risk analysis in the coming decades. It was held at the EFSA's 75th Advisory Forum meeting in 2020. GIS has been integrated been an integrated part of risk analysis since before it was called risk analysis, as exemplified by the famous map by John Snow of the water pumps in London during the cholera epidemic. Back in those days, information moved at the speed of John Snow on a horse, and risk moved at the speed of a woman carrying water buckets. Whereas today we live in a much larger, more integrated world where we have the both opportunity and obligation to see risk linked to processes on multiple scales, linked over larger differences, over larger distances, and where information can move at the speed of light and risk at the speed of a commercial airliner. So most people are in the field aware, but not always taking into account that risk factors that we measure might be dependent on what spatial scale they are being. Even the direction of an effect can change depending on the spatial scale, and different processes operate on different spatial scales. The same goes for temporal scale. The most common example I tend to use is how we find the locust swarms in China over the last 2,000 years to be linked to climate fluctuations. But what conclusion you would draw from the data depends on the temporal scale you're looking at, since the locusts tend to emerge from mudflats along rivers. These mudflats are largest after big floods, which tend to occur most often in wet decades, but they are also largest in dry years. So whether you would think locust swarms happened during droughts or wet periods depend on what temporal scale you would be looking at. This obviously then plays into everything that's all the risks that are linked to droughts, floods, and locust swarms, which includes famine and its companion war, which follow the same patterns over the same long time period. So how can we integrate these perspectives into risk analysis over the coming decades? Well, first I think we need to develop a conceptual framework where we are very explicit about the spatial scales of the effects and risk factors we measure and include. And we need to be aware that the only constant is change. Here exemplified by a study done by the Norwegian Science Committee on the invasive species of Pacific salmon moving into the Atlantic Ocean. The Pacific or pink salmon has been found to survive better in its oceanic phase in warm periods, and warm years thus see a larger return of pink salmon to Norwegian waters if the areas that are warm correspond to the areas they use during their oceanic 1 year. However, if we build our risk perspective on the observed data period, we run the risk of being spectacularly wrong, as the underlying system is not stationary. The temperature in the North Atlantic and Barents Seas are rapidly moving out of the data area. The observed range of temperatures are already behind us. And if we extrapolate the observed or modeled risk of Pacific salmon entering Norwegian Scandinavian waters over the next 50 years, Well, we need to be aware that we are moving outside the observed area, and thus our extrapolations might not be warranted. And then thus need to be dynamically and continuously updated based on a mechanistic understanding of the underlying processes. How to achieve a mechanistic understanding then of the underlying processes? This is, in such a complex world, this is dependent on an intimate knowledge of many different systems. This can only be achieved of drawing and integrating the knowledge of people who work on the different levels of every different system. But to get their knowledge integrated into the final analysis, we need a multi-directional information flow where the people who know each system become interested in and capable of participating in analysis, and where the people doing the analysis listen to the people who are informed about the specific system. One tool in particular here could be to promote the use of shared freeware, empowering people to understand and participate in analysis of their own parts of the system on their own level, to better understand what the needs are and what ideas can be provided for people working on more aggregated levels of analysis. An example include the Science Committee's members work on chronic wasting disease in the Norwegian mountains, where farmers owning livestock, administrators, scientists, and hunters have been collaborating with each their specialized knowledge to both control, model, understand, and effectuate control of the afflicted reindeer populations. This brings us further to the next step, which is interdisciplinarity, demanding more specialists, and in particular specialists and generalists working together. One of the biggest hurdles towards achieving this is the use of, well, essentially cloaking simple ideas in a complex bureaucratic language, which is the part where I believe we as managers and scientists and risk analysis performing specialists have a lot to contribute with. Keeping the ideas complex, but cloaking them in a simple language used to explain them in a concrete fashion is probably of great importance. One example here is the fairly successful predictions of the expanding range of wild boar into Scandinavia. However, this is bringing us to an end for today, and I thank you all for your attention and patience.